Good morning. I can hear you, Professor. I can hear you.
Speak.
I can hear you now.
You can hear me now? Ethar, can you hear me?
Yes.
Okay. Oh, okay, good. My ear things just went pop. So I have to go get a new set of earphones. For some reason or other, my microphone doesn't work unless I have the earphones in. Everybody is hearing me, correct? Benita, you hearing me? Benita, thumbs up if you hear me.
Professor, I can hear you. I have I sent you an email. I have an internet outage in my area.
Yes.
So I can't be on my laptop. I'm on my phone, so I can't turn on my camera.
No, it's not, that's fine. Don't worry about it.
All right.
Just the fact that you're here is good enough. Yeah, I did remember that. I think I told you to, were you able to complete the assignments, Natalie?
Yes.
Okay, good enough. And again, those of you that have me for lab in the afternoon, you're on your own from now until Tuesday when you do the presentations. Okay.
Just real quick about the lab. Do we have to connect the curves, like the dots on the curve, to?
Yes.
Okay. Perfect.
And you're going to do that. You're not going to use the straight line curve.
Yeah.
Okay. All right, guys, I got to go find my PowerPoint. Anybody confused about on Tuesday's lecture? Anybody confused about that? Any questions about Tuesday's lecture? Because Tuesday is where we went through the meat of the problems. No questions, guys? All right, where we're starting from today. We ended last week on Tuesday on oxidation numbers. Basically, we're going to use those numbers to do extremely hard balancing equations. So that's where we're going on from here. Okay, we're going to share screen, and you should all be seeing the screen right now. Is that correct?
Yes.
Yes.
All right. As a review, what I'm going to do when I'm determining the oxidation numbers, I'm going to first look at the ions that are formed. If it's a monoatomic ion, that will be its oxidation number. Like, for example, in C here, I've got PbCN4. That's written wrong. I've got PbCN4, which means each CN has a -1 charge. So to balance that molecule off, lead has a +4 charge. So I already know what lead's oxidation number is. Now I got to figure out what CN is. Normally speaking, nitrogen is going to be a -3, especially, excuse me, -3, especially when it's next to carbon. So the whole thing, the CNs are equal to a -1. If the nitrogens are worth a +3, then carbon's oxidation number plus nitrogen's equals a -1. So if nitrogen is a -3, I have to ask myself, what do I add to -3 to get to be a -1? Carbon's is a +4. HgNO2. Generally speaking, guys, you want to look for the hydrogens and the oxygens because they have the most stable oxidation number of -2 for oxygen. For hydrogen, it's a -1 if it's next to a metal. It's a +1 if it's next to a non-metal. So I look and see HgNO2. NO2 has a -1 charge, so my Hg has to have a +1 charge. NO2 is a -1 charge.
Where?
So oxygens have a -2 charge. -2 times 2 of them, I have a total negative charge of -4. So what has to be added to -4 to equal a -1? +3. That's how oxidations our oxidation numbers are determined. Now we need these. We need these because we need to determine oxidation and reduction numbers. Elements and ions change their oxidation states by either gaining or losing electrons. If I have zinc going to zinc +2, that zinc is losing electrons.
Oof.
By definition, loss of electrons is oxidation.
Oh, baby.
On the other hand, I can have a reduction. If a substance gains electrons, that is a reduction.
Oh, baby.
H
No,
plus
baby.
went to neutral hydrogen.
No.
So since it's gone to neutral hydrogen,
No.
it has gained an electron. Are you seeing that, ladies and gentlemen? Anybody confused about gain and loss of electrons at this point?
Stop.
Zinc went to a +2 oxidation number from 0. In order to do that, it needs to
dropped it.
lose 2 electrons. Hydrogen, on the other hand, is a +1 charge. It's going to a neutral charge. So in order to do that, the H plus has to gain electrons. Now, you cannot have an oxidation without a reduction. You cannot have a reduction without an oxidation. If one happens, the other has to happen as well, because we can't have either electrons being generated or electrons being destroyed. You can't have that. That doesn't happen in the world. So if there's an oxidation reaction, it's accompanied by something that's going to accept the electrons that the oxidation creates. On the other hand, if the reduction is grabbing electrons, it's grabbing them from somewhere. The somewhere it's grabbing them from is the oxidation. Very confusing. I need to have all of your attention here. because these are confusing terms, and they're confusing terms. And I really wish I had the person that decided to do this. And I wish I could have him right in front of me so I could slap him silly. We're talking English here, ladies and gentlemen. Chemists should never be allowed to use the English language because they screw it up. All right. Now, if you have a substance that is reduced, because of that fact I mentioned a few minutes ago about an oxidation being accompanied by a reduction, if something gets reduced, it causes something else to become oxidized. So when something is reduced, it is also the oxidizing agent.
Where am I? Yes.
Benita. Benita, thank you, Benita.
Sorry.
All right. So if something is reduced, it causes something else to be oxidized. So the substance being reduced is the oxidizing agent or oxidizer. All right. If another substance gets oxidized, it causes something else to be reduced. So the thing that's oxidized is the reducing agent or the reducer. Anybody confused by that? We're just talking English language here right now, guys. And you have to realize that something can be called in two different fashions. If it's reduced, it's the oxidizing agent. If it is oxidized, it is reducing agent. I will try and use reduced or oxidized. Now, the way you remember what's oxidized and what's reduced, either Leo goes Gur, loss of electrons is oxidation, gain of electrons, reduction. Or you can use oil rig. Oxidation is loss of electrons, reduction is gain of electrons. Mnemonic devices to figure out whether something's being oxidized or reduced. Again, you cannot have an oxidation reaction without a reduction reaction. Questions on that, ladies and gentlemen? We good, Natalia? Other than you yawning at me? Benita, we good?
Yes.
You're able to get through, were you able to understand that through all right.
Yeah.
Sachari, are you understanding this?
Yes.
All right. Okay, look at that monster there, guys. How are you going to ever balance that monster? You got 3 reactants, 3 products, things going every which way. You got 2 amounts of oxygen in 2 different compounds in both sides. How are you going to figure out what gets put where? We're doing this by our oxidation reactions and our reduction reactions and being able to balance the electrons. Look at that. The reaction you see on the bottom is the balanced equation. How long do you figure it would take you without some system to figure out those particular coefficients? So we're going to use the half reduction method. We're going to assign oxidation numbers to determine what's oxidized and what's reduced. And once we do that, we're going to write the oxidation and the reduction half reactions. This means we're just going to take whatever is being oxidized and determine what's happening to that, balance it, and whatever is happening to the reduction, balance that. Then between the two of them, we're going to balance the electrons. And that will give us the big, long, complicated balance reaction. So what we are going to do, we're going to assign oxidation numbers, and we're going to figure out what's being oxidized and what's being reduced. And then we're going to write the oxidation reduction half reactions. We're going to balance the half reactions. First, we're going to balance all the elements other than H and O. We're going to balance the O's by adding waters. The same number of oxygens that are on one side of the equation, we're going to add that many waters to the other side. But this is going to futz up our hydrogens. So we then, to the opposite side of the waters, we add H pluses and balance the hydrogens. Last thing we're going to do is we're going to balance the charge by adding electrons. Then we're going to multiply the half reactions to see that our electrons gained and lost are the same. I add the half reactions. I subtract things that appear the same on both sides. I make sure the equation is balanced according to number of atoms. And then I make sure the equation is balanced according to charge. Then I plug the numbers back into the original equation. Let's do it simple first. I have SN plus iron chloride going to SnCl2 plus Fe. This is a simple one that you can generally balance on your own. You would normally just put a 2 in front of the iron, a 3 in front of the tin 2 chloride, then you'd have to put a 3 in front of the tin and a 2 in front of the iron, you're balanced. We don't need to do this procedure for something as simple as this, but we're going to use this simple thing to try and explain what we're going to do with the complicated thing. First step, assign oxidation numbers. My tin is by itself, no charge. Iron chloride, my iron has a +3 charge. Chloride, I have 3 of them, it has a -1 charge. I'm sorry, chlorine has a -1 charge. Tin has a +2. So immediately I see that my tin metal is losing 2 electrons to make tin +2. So I have a reduction. My tin is losing 2 electrons to make tin +2. My iron, on the other hand, is gaining 3 electrons to go from Fe +3 to Fe0. I'm sorry, gain of electrons is the reduction. So the Fe is being reduced. The iron is being oxidized. It is losing electrons. Losing electrons, oxidation. Gaining electrons, reduction. Chlorine. Is anything happening to the chlorine? Not a thing now. Not a thing is happening to chlorine, so it's not going to be figuring in to our half reactions. I got to see what's happening to my tin. I got to see what's happening to my iron. First, determine what's changing. My tin and iron are changing. Next step, I write the half reactions. My tin is going to tin +2. I need to balance the charges. So I'm going to put 2 electrons on this side. The 2+ from the tin plus the 2 negative charges from the electrons balances the right side to be 0. The left side is 0. So Jana, if I have Fe plus 3 going to Fe neutral, which side do I have to add the electrons on? And how many electrons do I need to make sure that my charges are balanced?
It would be on the product side.
If I put it on the product side, if I add electrons over here, then I've got plus charges on this side, minus charges on this side. Are they ever going to equal each other?
Oh, yes. No.
Pluses and minuses equal each other?
No, sorry.
So which side do I have to add the negative charge to get back to 0?
Oh, it's going to be on the reactant side, and then it's going to be electrons.
How many?
3 electrons.
3 electrons. So I'm going to put 2 electrons on the side of the tin, 3 electrons on the side of the iron ion. I have no H's or O's to worry about. I balance the charges with my electrons. Fourth step, I got to balance the electrons. Now, I have the tin giving 2 electrons and the iron sucking up 3. So, Rhea there? Is Rhea here today? Anaya?
Yes, I'm here. Ria's here.
Okay. Rhea's here? Okay, Rhea, we'll go. I asked you first. We'll go with you. Rhea, if tin produces 2 electrons and iron sucks up 3, are those balanced?
No,
So what do I have to multiply the 2 by, and what do I have to multiply the 3 by to get them to be equal?
you have to multiply 2 times 3 and then 3 times 2.
So what I've got to do is I've got to multiply the entire half reaction. I got to multiply the tin reaction by 3. I got to multiply the iron reaction by 2. So this gives me 3 tin metals yielding 3 tin ions plus 6 electrons and 2 iron ions plus 6 electrons yielding 2 iron metal atoms. I add everything up, cross out my electrons, and I plug it back into my original equation. So I get 3 SNs plus 2 FeCl3s yielding 3 SnCl2s plus 2 irons. My equation is balanced. Fairly simple one, guys. Anybody have any questions so far?
Can you go back to the previous slide when you added like everything?
I'm adding this reaction with this reaction and creating this one. So the 3 SN zeros go down, the 2 Fe plus 3s go down. There should be a plus 3 up there. The 6 electrons go down. That yields 2 SN plus 2s plus 2 Fe's plus 6 electrons. I've got 6 electrons on both sides. I can cross them out. And then I just plug the coefficient up there, this coefficient up there, this coefficient up there, and this coefficient up there. So I put it into the original equation. Everything is balanced. Questions, ladies and gentlemen? Oh, this is a piece of cake, isn't it? And isn't this the simplest thing you ever saw?
Yes.
Wait. It gets more complicated. Remember that original reaction. Okay? We got to figure out what's being oxidized and what's being reduced. So I have permanganate, MnO4 minus. I have a magnesium over here. So if I'm looking at MnO4 minus, I've got oxygen at a -2, and my overall charge is a -1. So I have 4 oxygens. I don't know what manganese's charge is. So I have X plus 2 times -4 equals a -1. X plus -8 equals a -1. What is the charge on the manganese? Araceli. X plus a -8 equals a -1. What do you have to add to -8 to get it to equal to -1?
Would it be plus 7?
Plus 7, exactly. So the oxidation state of my manganese is going from +7 to +2. I have to add electrons to the MnO4 to make Mn plus 2. So my MnO4 minus is being reduced. I'm adding electrons to it. On the other hand, I've got C2O4 2 minus. Again, I have 4 oxygens, so 4 times a -2 is going to be -8. So in this case, since I have 2 carbons, 2x plus a -8 equals -2. If I have 2x plus a -8 equals a -2, can you see that 2x is equal to a +6? Do you see that, ladies and gentlemen?
Yes.
I'm going to do a survey around. Everybody good with this? We good? All right. So simply now, Anaya, what's X equal to?
3.
+3. All right. Keep that in mind. So on the left side, my carbon is equal to a -3. By the same token, I also have my carbon at CO2. So I have to have my X, 1 carbon, plus 2 times a -2 equals 0. What does my X equal? Come on, guys, simple algebra. Somebody shout out the answer.
4.
Thank you so much. Thank you so much. So my carbon is going from a +3 to a +4. My carbon is actually losing electrons to become oxidized. So now I know the manganese is being reduced and my carbon is being oxidized. My half reactions. My C2O4 is going to CO2. C2O4 is going to CO2. Now, the first thing I have to do is I have to balance the carbons. I have 2 on the left, 1 on the right. I have to put a 2 on the in front of the carbon dioxide. Now all the elements are balanced. 2 carbons left and right, 4 oxygens left and right. I have to balance the charges. I have 2 minus on the left. To which side do I have to add electrons and how many of them to balance the charge here? Ethan. Ethan,
Yes.
I've got 2 minus charge on the left. My right side is neutral. To balance the charge of 2 minus, on which side do I have to add electrons and how many of them?
You would have to add 2 electrons onto the product side.
Now I have 2 minuses on the right, 2 minuses on the left. I am balanced. Okay, now we're going to deal with my MnO4. My MNs are balanced. That's okay. However, I have 4 oxygens I need to balance. My rules say if I want to balance oxygens, I have to add waters to the other side. I have 4 oxygens. I have to add an equal amount of waters to the other side of my equation. But now, do I have something that's not balanced? Natalia, do I have something in that bottom equation that is not balanced? I'm not hearing you, Natalie.
No?
What's not balanced?
Hydrogen?
The hydrogens aren't balanced. My rules say if I have waters on one side, I can balance the hydrogens by adding acids to the left. How many acids am I going to add? How many H pluses am I going to add? I'm going to add 8. So I get 8 H pluses plus MnO4 minus yields Mn2 plus 4 waters. Now this becomes a little bit tricky. I got to figure out, I got to balance my charges with electrons. Okay, I have 8 pluses from the H plus. I have 1 minus. So my left side has basically 7 pluses. My other side, my Mn, has only 2 pluses. So on the left, I have 7 pluses. On the right, I have 2 pluses. What do I have to add to 7 plus to equal 2 plus? That wasn't the right answer, Natalie. And Natalia. I have 7 plus on the left. I have 2 plus on the right. Which side do I have to add minuses to get the 2 equal?
Left.
I have to add them to the left. 7 E's or 7 plus 5 electrons will equal 2 plus. So I'm going to add 5 electrons to the left side. Both of my half reactions are now balanced. I have to put them together. Are my electrons balanced? Jenna? Are my electrons balanced in these 2 half reactions?
Yes.
I've got 2 electrons on the top one, 5 on the bottom. Are they
Nope.
balanced?
Nope. No, they're not.
All right, Jenna.
Sorry.
How am I going to balance them?
You need to add 3 more electrons to the top one.
But you can't add them. You have to do it by multiplication.
Can multiply. Oh, multiply by 5 on the top and multiply by 2 in the bottom.
Exactly. We have to get our electrons balanced. So I have to multiply the top reaction by 5, the bottom one by 2. If I do that, my 8 goes to 16. There's 2 in front of my MnO4, 2 in front of my Mn2 plus, and the waters become 8. I add these 2 together. I get 10 electrons plus 16 H pluses plus 2 MnO4s plus 5 C2O4s, yielding 2 Mn2 pluses plus 8 waters plus 10 CO2s plus a partridge in a pear tree. Cancel out what's the same? 10 electrons, 10 electrons. Now, all I have to do is plug in these values into my original equation, and it is balanced. Questions? Questions, guys?
I have a quick question. How did you get 5E? Just real quick.
How did I get 5E? We are talking
Yeah.
about back here. I'm sorry. Back here? Nope, nope,
Yeah.
nope, nope. How did I get the 5E? Okay. How many pluses do I, who's asking the question?
Jennifer?
Jennifer, good. How many pluses do I have from the 8 H pluses?
Like total with the 8?
Mm-hmm.
Okay.
I have 8 pluses, correct, Jennifer?
Because there's 8H in front of it. Okay.
How many minuses do I have?
Would you say 1?
1. 8 plus 1 minus gives me how many? Gives me how many
7.
pluses?
7 in total.
7 pluses. Now let's look to the other side. How many pluses are total on the other side?
I see a +2.
So I've got 7 pluses going to 2 pluses. What do I have to add to the 7 pluses to equal 2 plus?
-5.
Which is where the electrons come in.
Okay. So you just pay attention to the charges and then the.
You have to pay attention to the charges, yes.
Okay, thank you.
So we've gone through. We have balanced this. Am I in acidic conditions or am I in basic conditions?
Acidic.
I have H pluses here. I have H pluses there. That means I'm in acidic conditions. These reactions work in acids and they work in bases. So if I want to balance this in basic conditions, the first thing I do is I solve it under acidic conditions. I do everything I have done up to this point. Then what I do is I add OHs to get rid of all the H pluses. If I add H plus an OH minus, I make water. So if I add 16 OH minuses to 16 H pluses, I have made 16 waters. But if I add 16 OHs to the left side, I have to also give them to the right. So I'm going to, so I am going to add. I will add I'm going to add 16 OH minuses. But if I do it to one side, I have to add it to the other side. I add these two reactions up. I get I add these two reactions up and I get $16 waters plus that yielding 16 OH minuses plus now look, I have 8 waters on the right side, 16 on the left. This 8 on the right cancels 8 of the 16 on the left. So I can rewrite this to be eight on the left and none on the left. None on the right, rather. So I have now balanced my reaction in base as well. We've got a couple more of these problems to do, and we're going to work through it. The simple thing, if you have it solved in acid and you want it in base, add the same amount of OH minuses to as you have H pluses to both sides, cancel out the waters, and you're done. When it doesn't balance, sometimes you're going to go through this and it will not balance. So you got to do a few tricks to make it balance for you. I have this reaction, KMnO4 plus KCl plus H2SO4 yielding MnSO4 plus K2SO4 plus water plus Cl2. Okay? Again, figure out what is balanced. Figure out the oxidation states. Again, I have MnO4 going to Mn plus 2. So my Mn is being reduced. It is going from a plus 7 to a plus 2. My Mn is being reduced. Okay, chlorines. Oh, look at the chlorines. We're going from a -1 to a 0. So my chlorine is being oxidized. My chlorine is producing, wait. Yeah, my chloride is producing producing electrons to go to Cl2. So I've got KCl going to Cl2. I've got MnO4 going to Mn plus 2. Half reactions. What is really happening? My potassium's not changing, so I'm going to leave it alone. I'm not going to touch it right now. My sulfate isn't changing, so I'm going to leave it alone. All I'm going to do is balance the ions. So in reality, I have Cl -1 going to Cl0. I've got MnO4 -1 going to Mn2 plus. Okay. Are my chlorines balanced? Okay, Benita, Sachari, and Ria. Sachari, are you there? Ria, are you there? I see you, Ria. You may want to move your thing down so I can see you. Vanessa, are you there? I'm seeing a ceiling.
I'm here.
Vanessa, Vanessa, are my chlorines balanced in the top reaction?
Nope.
What would I have to do to balance my chlorines?
We're trying to get them
What?
to
First step.
zero.
First step, not yet. First step, we have to balance the atoms. We have to balance the atoms first. I have how many on the right and how many on the left? Chlorines.
You have -1 on the left and 0 on the right.
Chlorines.
Chlorines.
How many chlorines do I have on the right and how many chlorines do I have on the left?
Would it be 2 on the left?
2 on the left?
Yeah. I mean, on the right, I'm sorry.
Thank you. 2 on the right, 1 on the left. How do we balance them?
Could you add another on the left?
Not adding, no adding. We don't add in balancing equations, we
Oh, okay.
multiply.
So you would multiply the right side by -1. Yeah.
If I multiply the right side by -1, that gives me, first of all, you can't do coefficients of -1. All I want you to do is balance the chlorines. How many chlorines are on? You said 2 are on the right, 1 is on the left.
Mhm.
What do we put in front of, what numbers do we put in front? All I want you to do is balance the chlorines. Do not think of negative numbers.
So just a 1 in front of the chlorine.
If I put a 1, they're still not balanced. Emily. Are you there, Emily?
Yeah.
I don't see your face.
I'm
Where's
not
your
home
face?
right now, so I don't have a camera,
All
but
right.
you multiply by 2.
I multiply the Cl minus 1 by 2. So I have 2 Cl minuses yielding Cl2 0. Now, I have 2 in front of this chlorine. Emily, what's the total negative charge on the left?
2 negative.
2 negative. What do I have to add to the right to balance that 2 negative?
2 electrons.
2 electrons. So my new half reaction is going to be 2 Cl minus yielding Cl2 plus 2 electrons. Are we good with that, everybody? Are we good, guys? Okay, Jordan. Jordan, are you there?
Yes.
All right, let's look at the bottom one now.
Okay.
Are my MNs balanced?
No,
I got how many on the left?
just 1.
How many do I have on the right?
Oh, sorry. There's 1 and 1.
1 and 1. Okay. Are my oxygens balanced?
No, there's no oxygen on the right side.
So I have to add the same number of waters to the right as I have oxygens on the left. How many waters am I adding?
4.
4 H2Os. This now means I have 8 H's on the right. How many H pluses do I add to the left then?
You said there's 8 on the left?
8. There are 8 now because you just added 4 waters.
Mm-hmm.
So 4 H2Os. That means there are now 8 H's on the right. How many are on the left?
None, so you have to add 8.
8 H pluses. So I'm adding 8 H pluses. Now, I'm at this stage. Now I'm at the stage where I'm balancing charges with electrons. Ether. Ether,
Yes.
how many negative charges do I have on the left of the arrow here?
For the O?
How many negative charges do I have contributed by my
No.
2 Cl
One.
minuses?
-1.
How many of the negative ones are there?
2.
So what's the total negative charge on the left?
Would be 2.
2 minus. I have to balance that with electrons on the right. So how many electrons am I adding on the right side of the arrow?
2, I guess.
I'm adding 2 electrons. Okay, Sachari.
Yes.
All right, show your face, Sachari.
Okay. What's the question?
Show your face fully down.
Is that really necessary?
Well, I need to see your, I can't tell just by looking at your eyes whether you're understanding what's going on. Thank you. So, how many pluses do I have on the left side?
1, 2. Oh, is the plus in front of the 8 count?
Yes, it does.
So 2, right?
Where are you counting 2 pluses from?
Are we looking at the signs in front of the?
We're looking at the second reaction.
Yeah.
We're looking at that reaction.
Mm-hmm.
How many pluses do we have on the left side of that arrow?
Is it 1?
No.
3?
Where are you getting 3?
I'm like looking at the pluses. Is it not 2?
How many pluses are there from the 8 H plus?
1.
How many of the ones are there?
1.
What does the 8 in front of H plus mean, Sachari?
It's a 1, and so that's why I said 2.
It's not a 1. What does the 8 in front of H plus mean? How many H pluses do you have?
8.
So how many pluses do you have from those 8 H pluses?
8.
So we have 8 plus what is the contribution from the MnO4? How many minuses does it have?
Is it 1?
1. So I have 8 plus a negative 1. What is the total positive charge on the left side of the equation?
7.
Plus 7. How many pluses do I have on the right side?
Is it 4?
What's the charge on water?
There's no charge.
So are there any pluses from water?
No.
What else do you have on the right side?
2 plus for Mn.
How many of them are there?
1.
So what is the total positive charge on the right side of the arrow?
1.
You just said that the Mn had a +2 charge on it.
Oh, sorry, 2.
So I'm going from 7 plus to 2 plus. How many electrons do I have to add to which side of the arrow? Going
5.
from 7 on the left to 2 on the right.
5
Which side?
to the right.
If I add 5 to the right, If I add 5 to the right, this means I have a +7 on the left, a -3 on the right. Are they balanced?
One moment, please.
I don't have a moment.
I'm sorry, it's because my mom was talking to me. What was the question?
If I have 5 E's plus 2 pluses, that makes 3 minus on the right. Does that balance with 7 plus on the left?
No,
So where do we have to add the 5 E's?
to the left.
Jordan, are my electrons balanced?
Yes.
How many electrons do I have coming from the chlorine half reaction?
2.
How many do I have from the bottom reaction?
5.
So are the electrons balanced?
No, so you would multiply the top by 5 and the bottom by 2.
That gives me 10 Cl minuses yielding 5 Cl2s plus 10 electrons, bottom one 10 electrons plus 16 H pluses plus 2 MnO4 minuses yielding 2 Mn2 pluses and 8 waters. I then add the two reactions together and I come up with this monster here. The only thing that's the same are the 10 electrons. I put them up there into the top. All the coefficients you see down here, I put into the top equation. Am I balanced? Am I balanced?
No.
I have 2 potassiums from the KMnO4 and I have 10 from the KCl. I only have 2 on the right. When after you've done the half reaction, don't mess. Do not mess with the numbers you have just made. I generated the 2 from my half reaction in the KMnO4. I generated the 10. As a matter of fact, I put the H2SO4s in there. This one also, this MnSO4, I did not create from the, or I created from the oxidation half reactions and the 5Cl2. This one I haven't messed with. I've got 2 plus 10. What number goes in front of the K2SO4?
A 6.
Now, 2 Ks plus 10, 12 Ks on the right. 2 Mns, 2 Mns. Okay, I'm going to treat the SO4s as a unit. I got 2 times 4 or 8 oxygens, 8 times 1, 8 oxygens. 10 times 1 Cl, 10 Cls. 5 times 2, 10 Cls. 8 times 2, 16 hydrogens. 8 times 2, 16 hydrogens. 8 SO4s. I got 2 SO4s there, 6 there. I am balanced, ladies and gentlemen. Now, note something. What's the number in my half reactions? Do you note the number in front of the H plus? What is that number?
16.
But the compound, the only place where I can put the H pluses is in H2SO4. I need 16 H pluses. I only need to put an H in front of the H2SO4 because there are 2 hydrogens there. Try to balance. try to balance your equation. If after you do the half reaction and it does not balance, you want to manipulate the coefficients of the chemicals you have not already changed.
Is that the last example?
No.
Okay, cool. Good.
This one maybe though. Got to figure out what's being oxidized and what is being reduced. My nitrogen. NO3 is a -1. Oxygen's contribution is a -2. So what plus -6 equals a -1? Nitrogen's going from a +5. In the case of NO, oxygen's a -2. The nitrogen has to be a +2. So my nitrogen is going from a +5 to a +2. Iron, +3, going to a +2. I've got my oxidation and reduction reactions. So I have my NO3 going to NO. I've got my iron +3 going to iron +2. All right. Are my ends balanced? Natalia, are my ends balanced? Looking at that reaction, are my ends balanced?
I would say yes.
Okay, how about my oxygens?
They're no.
So how many oxygens do I need to add to what side?
Right.
How many? Put your fingers up. I'm not hearing you too well.
3.
All right. I have 3 oxygens and 1 oxygen. So how many more oxygens do I need on this side?
You need 3.
I need 3, but I already have 1.
Oh, sorry, 2 more. Yeah.
So I'm going to add how many waters?
2 waters.
2 waters. Okay, I now have 8 hydrogens on my right. How many H pluses do I add to the left?
You need is it 4?
I need to add 4 H pluses on the left. So my numbers are balanced.
Yes.
I just need to balance my charges. Okay, I have how many negatives?
You have
Wait, why isn't this working? NO3 going to NO. Yeah, hold on a second. NO3 minus. Oh, yeah. +3, I need 3 electrons. Going from +5 to +2. Sorry, I need to add 3 electrons. Okay, Natalia. How many pluses do I have on the left?
You have 4.
How many do I have on the, no, pluses? 4 pluses.
Right.
I have to add the negatives in there. So what's my total charge on the left side? 4 pluses plus 1 minus?
It's 3.
3 pluses.
Yeah.
Right?
Mm-hmm.
So what do I have to, how many electrons do I have to add to the left side?
You have to add
I
wait,
have
no,
I have a total 3 plus
yeah,
on the
you have
left
to add
side,
3
0 on the
electrons.
right.
Yeah, 3 electrons, so they cancel out and it's 0 equals 0. Okay.
Okay.
Mhm.
Now I've got Fe2 plus going to Fe3 plus. Might as well stick with you.
So you have,
Which side do I have to add the electrons? Left or right?
I mean, you have plus 2 on the left side, right? Just 1, and then plus 3 on the right side.
Which side do I have to add the electrons?
Is it to the, oh, to the right? Just
To
1.
the right side?
Mhm.
Are my electrons balanced?
Yes. No. No.
So what do I have to do to the bottom equation?
Multiply by 3.
So this means the electrons are now going to balance out, as well as the ions. So I have to plug these numbers into my original equation. I have Cr2O7, 2 minus, plus an iodide, yielding IO3 minus plus Cr3 plus. Jenna, what is my first half reaction?
The Cr2O7 2 minus yields Cr2 and O7. Kind of.
No, look at what is this yielding? What's the chromium making?
Cr3 plus.
Cr3 plus. Okay. So this is my half reaction. Okay.
Mhm.
Now, Jenna, sticking with me.
Mhm.
Are my chromiums balanced? Are my chromiums balanced?
No.
So what do I have to put where?
You need to multiply the Cr3 plus by 2.
Okay.
There's 2 each side. Mhm.
All right. Now let's look at the oxygens. Are my oxygens balanced?
No.
What do I have to add to which side?
7 oxygens to the right side.
How do I add oxygens? In what form?
H2O.
So I have
Or
to add
water.
7 H2Os. Now, if I've added 7 H2Os, are my hydrogens now balanced?
No.
What do I put on the left side?
7 hydrogens. No. H2Os.
How many hydrogens is H2O?
2.
Yeah, so how many in 7 H2Os?
14.
So I put 14 H
Got you,
pluses on the opposite side. Now, I have 14 H pluses, 14 pluses, and 2 minuses.
Mhm.
What's the overall charge on the left side of my equation?
2. 0.
14 pluses and 2 minuses.
Oh, sorry. 12. Sorry, I was just looking at the pluses.
So I have 12 pluses on the left. How many pluses do I have on the right?
3. 3. 3.
What's the
1.
coefficient in front of the CR?
Sorry, say it again.
What's the coefficient in front of the CR plus 3?
2.
So what's the total number of positives on the right?
2.
No. 2 times,
3. 6.
if we have 2 chromiums, each chromium has a plus 3. That means there's a total of 6 positives on the right side.
Hmm.
So I've got 12 pluses going to 6. Does that make sense, Jenna?
Yes. Sorry, I'm caught up now.
I got 12 pluses going to 6. To what side and how many electrons do I add?
To the right side, you need to add 6 electrons.
If I add them to the right, I now have 2 times 6 pluses plus 6 minuses. I have no charge on the left. I still have 12 pluses on the right, on the left.
So you need to add 12 electrons to that side to make that also a neutral charge.
If I do that, that means I have 12 pluses minus 12 minuses.
Mhm.
I have 0 on the left and 6 on the right.
Hmm.
This is what you just told me to do. You told me to add 12 electrons to the left side. I have 12 pluses plus 12 minuses. There's no charge over there. I still have 2 times 3 on the right. So how many electrons do I have to add to a positive 12 to equal a positive 6?
Oh. Just 6 electrons.
I didn't hear you.
6 electrons.
I've got 6 E minuses. So 6 E minuses plus 12 H pluses, 6 E minuses plus 14 H pluses would give me 8 minuses plus a negative 2, 8 pluses rather, plus a negative 2. I have 6 plus on the left side. I have 2 times a 3 plus 6 plus on the right. I'm balanced here. Okay.
Mhm.
All right. Now, Ethan, are my iodines balanced?
They are not. There's 2 iodines on the left side and
So what do
one
I
on
have
the
to do
right.
in front of the IO3?
You have to add, well, you have to make a coefficient 2.
Thank you. So how do I fix my oxygen problem, Ian?
Wait, you add, okay, so you add H, like, wait, H, yeah, you add like 3 H2Os.
I'm going with that. If I add 3 H2Os on my left, how many H pluses do I have to add on my right?
You have to add 3, or no, 6.
6 H pluses.
Yeah.
Now I got to figure out about my electrons. I have
Well, let's see, the left side is neutral, and on the right side, let's see, 2 IO3, so 6 and so is the right side, actually. Wait. Wait, oh wait, the IO3. No, wait, that's okay. The minus is charge level, so you actually have like a +4 charge on the right side right now.
And how many on the left?
Well, 0. Like
So
no
how many
charges.
electrons do I have to add to what side?
On the right side, you need to add 4 electrons.
Now, I have to balance my electrons. Okay? If I have to balance my electrons, I've got 4 and 6. What do I have to multiply the top one by? And what do I have to multiply the bottom one by?
Wait,
What's the common multiplier between 6 and 4?
Like, oh, is it 2? Like, oh wait, is it 6?
I've
Like
got
12,
to get
12,
my 12.
12,
I'm
yeah.
going to multiply my first equation by 2. I'm going to multiply my second one by 3. I do that monster out. And this is what I get for my chromium. This is what I get for my iodine. I add the 2 together. I got 70 H pluses on the left side, 72 on the right. Subtract the 2 out, that leaves me with 2 H pluses on the right. My electrons cancel out, and I have 36 waters on the left, 35 on the right. Those cancel out, so I have 1 water on the left. I add them together and cancel out the common ions. I get everything balanced. Guys, I would strongly suggest you look at the video. You look at the video regarding oxidation, reduction, balancing equations. Practice this. You are going to need a lot of practice because, guys, I've just spent about an hour going through this. What are the chances this is going to be on the test? I've got to get on here with talking about cells because ultimately that's what we're talking about in this chapter. And I need a break, so I'm going to call one right now. I will be back in 5.
Professor, I have a question.
I don't think he has his headphones in, so he can't hear you.
Okay, you back, guys? Oh. Are you back, ladies and gentlemen? Ethan, can you hear me?
Yep, I can hear you.
Okay. All right, the whole reason we're going through those oxidation reduction reactions is because they're going to become important when we go through and determine the voltage of a non-standard cell. It's going to be extremely important that we have a balanced chemical reaction for it. And so now basically what we're going to talk about are voltaic cells, what you guys are going to call batteries. Now, what you think of as a battery. The difference between a cell and a battery is that a battery has multiple cells that are linked one to the other. If you've ever opened a car battery, you see that there are different compartments for the different cells. So if you look at a car battery, it's generally 12 volts. Each one, you have 12 of those cells, each delivering 1 volt. So these battery are cells that are linked together. A cell is just the individual segment that is transferring electrons from one side to the other. So what we're involving when we have a battery or a cell is we're getting a transfer of electrons. If we get an electrons transferred, that means we have an electron flow. If we have a flow, we can make a circuit, which gives you the electricity. So we have a redox reaction, reduction and oxidation going on in the voltaic cell. Typical cell will look like this, and I'm going to blow that up for you. you are going to have a anode. An anode is where the oxidation takes place. It's producing electrons. Remember, oxidation, loss of electrons. Electrons go away. They flow towards the cathode. Cathode grabs electrons. The electrons react with the ions to make metal. So what's happening? We are getting a flow of the ions, the positive ions, towards the metal. And we're getting a flow. The metal is losing electrons, so the metal is going from neutral into being a positive ion. Now, the problem with this is we're producing pluses in this cell and we're taking them away in this cell. If we did nothing and we kept them separate, what would happen is the reaction would immediately shut down, because I've got, if I'm taking a plus out of this solution, I don't have pluses in here to react with the NO3 anymore, and the charges have to be balanced. So that is going to prevent any more electrons from flowing in this direction. Similarly, I'm building up pluses in this side, and I am not having enough negative ions to counteract that. So I have to have something called a salt bridge in between. The salt bridge is filled with positive ions and negative ions, because the electrons are being formed at the cathode. The positive ions are reacting and we're plating out metal at the cathode. But what's happening to replenish the positive ions in this solution? The salt bridge is delivering positive ions. At the same time, my metal's getting eaten up in the anode. So my metal is delivering zinc pluses, but to balance that out, I have negative charges that are in the salt bridge. So overall, what's happening in the cell? Because of the redox reaction, I have an oxidation occurring at the anode. Guys, the easy way to remember what's occurring at the anode and what's occurring at the cathode: oxidation and anode both begin with vowels. So the anode has the oxidation reaction. The anode is where you are producing electrons. Reduction, cathode, both consonants. So I have an oxidation reaction going on. It is producing electrons. Those electrons go through some sort of a work aspect, and they get delivered to the cathode. Because we've got a buildup of electrons, it's going to grab the positive ion from the solution, and that positive ion is going to plate out. I need to replace the positive ion, so the positive ion's going towards the cathode. I'm building up positive ions in the anode, so the negative ions go towards the anode. Again, Leo goes grr. Oil rig. Oxidation, loss of electrons. Reduction is gain of electrons. Now, again, if I did not have the salt bridge between the two of them, and if I wasn't replenishing the pluses in the cathode, and I wasn't replacing the negative ions in the anode, the reaction would stop. But since I have the salt bridge in place, everybody is happy. Electrons leave the anode, go towards the cathode. So ultimately, what's happening? In the anode, my individual metal ions are losing electrons. As they lose electrons, electrons are going up. That metal is getting dissolved into the solution. At the cathode, I'm building up electrons. So the ions are going towards the cathode and they are plating out on that particular electrode. Electrons flow from anode to cathode. Makes sense because the oxidation reaction is producing the electrons and the reduction reaction is sucking them up. At the anode, the metal is losing electron, so it is getting ionized and goes into the solution. At the cathode, the metal or the electrode is building up electrons. So the metal ions in solution are attracted to the negative cathode and can accept the electrons and plate out onto the cathode. If we didn't have anything, the circuit would stop because of the buildup of charges. We have the salt bridge. And the salt bridge permits flowing of ions back and forth. Negative ions flow towards the anode, positive ions towards the cathode. Consider the cell below and assume these working conditions. We're going to look at, I need to know direction of the electron flow, direction of the flow of the negative ion, direction of the flow of the positive ion, and positive other ion. Species being reduced, species being oxidized, reduction agent, oxidizing agent, cathode, and anode. If I am assuming these conditions, that I'm mixing lead with copper, I have to tell you, you're going to be able to figure it out soon, but I have to tell you what is happening. The copper is being reduced. So I've got copper plus two electrons going to copper metal. At the same time, my lead is being oxidized. My lead is going to lead plus two electrons. Now you can answer all of the questions. What is the anode? Remember vowels and consonants. What is happening at the anode?
It's losing electrons.
Which reaction, the oxidation or the reduction? You got a 50-50 chance here. Which one is occurring at the anode?
Oxidation.
Oxidation.
Oxidation. So I said that the lead is being oxidized, the copper is being reduced. Which one? Z is the lead anode. W is the cathode. Lead is being oxidized, so the anode occurs there. The copper is being reduced, so it occurs on W. Which way are my electrons flowing? Are they flowing A or B? Which way did I tell you the electrons flow? Do they go from the anode to the cathode or cathode to the anode?
From the anode to the cathode, so it's going to be A.
So the lead is the anode, so we're flowing in this direction. The answer is A. All right. I've got electrons flowing in this direction. I want to know which way the negative ions are flowing. Are they flowing C or are they flowing D? Remember, oxidation is occurring here. I'm creating electrons. The electrons are gathering on the cathode. So am I losing positive? In which side? Which side am I losing? I'm sorry, which side am I losing? I'm sorry, which side am I producing? Which side am I producing positive ions? Am I producing it on the anode side or the cathode?
Anode, because that's losing electrons to the other side.
So I'm producing electrons on this side. This must mean my lead ions are going into solution. I'm creating a buildup of positive charge. The NO3 has to go in the D direction to counteract that positive charge. So my copper, is my copper flowing out of the cathode, or is the copper flowing in and plating out the cathode? Remember, go ahead.
I'm sorry, can you repeat the question?
I need to know the direction of my copper. My copper is in solution here. Is my copper flowing from the electrode into solution? In other words, am I making ions from the copper, or am I taking ions from the solution and plating it out on the reduction?
I would say E, it's going onto.
Reduction. We're building up electrons, so those electrons are reacting with the ion to form copper metal. We are moving from the solution onto the anode. Okay. Direction of the lead +2. If the ions are flowing from solution onto the electrode in the reduction, what do you think is happening to the lead? Is it going H into solution, or is it also plating out?
I would say it's going to be the opposite. It's going to be going into the solution.
Remember, guys, the anode, we're losing electrons. If we're losing electrons, where they're coming from is the metal itself. If their metal is losing electrons, it's going to be positively charged, and it's going to go from the electrode into solution. So now we have to be specific. What is the species being reduced? Remember, we said the cathode, the reduction occurs. Is copper being reduced, or is Cu+2 being reduced? Which is gaining
Copper.
the electrons? The ion or the metal?
Ion.
So Cu+2 is the species that is being reduced. Similarly, is my lead being oxidized, or is my lead +2 being oxidized?
Lead +2.
Do you see any lead +4 in there? Remember, being oxidized loses electrons. If it loses electrons, then it has to go from a lower oxidation state to a higher oxidation state. What is being oxidized? Is the lead metal being oxidized, or is the lead +2 being oxidized?
Lead metal.
The lead metal is being oxidized because the half reaction, we're going from lead to lead +2 electrons. Again, another video I would strongly suggest looking at. Electrochemical cell notation. I am going to get through standard potential cells today. Basically, it's a short form. We write the oxidation half reaction on the left, the reduction on the right. Between the two of them, we put a double vertical line that separates the two half reactions from each other. Substances in different phases are separated by a single line. If they're in the same phase, they're separated by a comma. In the previous slide, we had copper +2 going to copper being reduced. And we had lead going to lead +2. So if I want to give a short cell version, short description of this, I'm going to put a double line in the middle. Oxidized reaction goes on the right, reduction reaction goes on the left. Double line in between separating the two cells. We go from the ions outward. So since the lead is being oxidized, I've got my lead metal going to be oxidized. My copper ion is reduced. Benita. Sorry, Benita, never mind.
Sorry.
Never mind. Jana,
Yes.
what is being oxidized? What is losing electrons?
Al, the aluminum.
Aluminum is losing electrons to become Al +3. So did I say the oxidation gets listed on the right or left?
It's going to be on the right because it's going to be Al 0.
Wait a second. I want to make sure I'm not saying something stupid. Which one, where did the oxidation go?
In this question,
In this question, which one, which side had the oxidation reaction?
it's going to be the one losing the electron, so it's going to be the lead.
Okay, so the oxidized reaction went on the left. So where is the aluminum going to go? Left or right?
It's going to go to the right towards the product side. Oh, sorry. It's going to go to the copper.
I'm asking on the short term, I'm not asking electron flow, Jana. I'm asking in the short term cell notation. Lead went to lead +2. That was an oxidation reaction. That got put on the left side of the double line. My question to you is, where does the aluminum go? Left or right side?
To the right side. Sorry. I don't think I really understand your question.
Jana, you just said a few minutes ago that aluminum was being oxidized, right?
Yes.
Okay. My previous example, the lead was oxidized.
Oh,
Which
like in
side of the
in
double
that
arrows
format?
did it? What? In this example, the
It's
lead was oxidized. So which side of the double arrow did it go on?
it went to the from the left to the right from the reactant.
We're not doing, Jenna, we're not doing circuits right now. All we're doing right now is cell notations. The lead was oxidized. So the lead goes on the left side of the double line. My question to you, you already said that the aluminum is oxidized. Which side of the double line do we note the aluminum reaction?
The left side.
The left side. Al is losing electrons, copper is gaining them. Oxidation reaction gets put on the left side of the double line. Reduction gets put on the right side. So the notation looks like this. Again, double line, ions are listed next, metals go on the far outside. This is basically trying to read this from left to right. Aluminum is going to aluminum +3, whereas copper 2+ is going to copper metal. Nickel and HCl reacting to make NiCl plus H2. Leonardo?
Yeah.
Okay. Can you tell me what is being oxidized? What is losing electrons? Is the nickel or the H losing electrons?
Is it the H?
H plus is going to H0.
Oh, so
Is
it's
the
the
H
nickel
plus
then?
losing electrons?
No, it's gaining.
So
So it's the nickel then?
the nickel metal is losing electrons to become nickel ion. Consequently, Leonardo, the H is it being reduced or oxidized? The H plus, is it being reduced or oxidized?
Reduced.
So if the nickel is being oxidized, what side of the double line does the nickel reaction occur? Left
On
or
the
right?
left.
So the nickel is going to appear on the left. The hydrogen is going to be on the right. But we can't have, hydrogen is not a metal. So we have to substitute something to act as the conduit to supply the H plus with the electrons. So we have another electrode in there, a platinum solid. Not the platinum, nothing's happening to. It's the iron, the H1 plus is going to the platinum, picking up the electron and sucking, going up into the air as H2. I need you to try these. 5 minutes. Jana, Jordan, Araceli, Sachari, Leonardo, I want you to do the first one. Natalia, Jenna, Benita, the second reaction. Athar, Manuel, Anaya, Ria, and Vanessa. Third reaction. Natalie, Emily, second reaction. I need to know, you need to do the cells for me. I need the short-term notation. are we doing?
I have a question.
Manuel, what's going on?
For the equation that you gave.
Which one did I
me,
give
the
you?
third
1, 2, or 3?
3.
Okay.
If Sn is going from Sn to Sn2 plus, that's reduction, right? Because
No.
it's gaining or oxidation.
It's oxidation. It's
Okay.
losing electrons to go from a neutral state to a positive 2.
Okay.
All right. So if that's the case, if it's losing electrons, which part of the cell is oxidation occurring?
And the Sn solid, correct? Or
You just said it's being reduced, Manuel.
okay.
Didn't I tell you to put the oxidation on the left?
Oh, okay. Wait, no. I'm sorry. So you said Sn from neutral to gaining, it's oxidation, and from gaining to
Whoa. You're looking at this as gaining charge, Manuel. No, it's electrons. Okay.
Oh, okay. That's what. Okay. So from
Sn0 going to Sn plus 2 is losing electrons. So it is being oxidized. Leo goes Gur. Loss of electrons, oxidation. Okay, Manuel?
okay.
The nickel, on the other hand, is gaining electrons to go from a +2 to a 0 charge. Gain of electrons, reduction. So which side is the tin going on? Left side of the double line, or the right side?
Well, you just said earlier that oxidation usually goes on the left, right? And
Doesn't
reduction
usually,
goes on the right.
always. Doesn't usually, it always goes on the left. So which one is going on the left, Manuel?
The tin, the Sn.
Tin is losing electrons. So I would say Sn 0, single line, Sn plus 2, double line, Ni plus 2, single line, Ni.
And you said oxidation always occurs on the left,
Okay.
or is always on the left side? I'm sorry.
Oxidation. The oxidation reaction in the cell notation will
Cell
always
notation,
be
yeah.
on the left.
Okay. All right.
Who's got the first reaction?
This is Jordan. You told me to do the first one.
Okay.
But I'm kind of stuck for the CU because it's just
that help you? Does that help you, Jordan? Just got a point for pointing out a mistake. Okay, Jordan, which one is being oxidized? Jordan?
Can you hear me?
Now I can.
Okay. So for the CU, is it being oxidized?
Is it losing or gaining electrons?
Gaining.
If it's gaining electrons, then it would have a negative charge since it starts at 0 and electrons are negative.
So it's losing.
If it's losing electrons, is that an oxidation or a reduction?
Oxidation.
So does it go on the left side or the right?
The left side.
So it would be Cu0 line, Cu2 plus, double line, Ag plus, single line Ag. Now who did the last one?
Equation 3 or the third one? Is that what you're asking?
No, second one, middle one.
I did.
Who's I did?
Nita.
Rhea?
Nita.
I'm sorry, go for it. What's-
Is the CR gaining electrons?
Yes, it is.
Okay, so that's the reduced one. And then the Mg is losing electrons, so that's oxidized. And then is it Mg and then the slash, I guess, Mg2 plus, and then the double slash, and then Cr3 plus slash Cr0?
Absolutely. 100%. 100%. Okay, I didn't get quite to where I wanted to get today, so it's about time for us to end anyway. So let's just end it right there. We're going to start off with standard cells on Tuesday. Any questions, ladies and gentlemen? If you didn't understand the way I explained it, then please look at the videos. Spent a lot of time on the cell. I spent a lot of time on oxidation reduction reactions. That should be a clue as to whether you're going to expect them in the test. If nothing else, it is now 20 after. So ladies and gentlemen, I will see you on Tuesday at 9:45 then, for those who want the help. If you don't understand something, phone me or come early on Tuesday.
Wait, did you say 9:45?
9:45 is always when I open up.
Okay, thanks.
Except today when I had my lab lopped over. That's all I got for you guys.
Professor, I have a question.
I'm here.
So before, when it was Cu with the 0, and then the other side was also Cu0, like, so you corrected it to be 2 plus, but would there ever be a situation when
No.
it's like 2 zeros?
No, you can't, Sachar, you can't do that because remember I told you with an oxidation, there has to be a reduction.
Okay,
So
got it.
one of the things had to be changed.
Okay, just making sure, because when I was doing it, like I made note, because I was confused, but then she said that, and then you ended up correcting it, but then I wouldn't have known how to do that. But I got it now. Thank you.
That was a mistake on my part that needed to be corrected.
Okay, no problem. Thank you. I'll see you Tuesday.
See you Tuesday.